10 lost civilizations that left behind technology we still can't recreate today. Number 10. Maya blue. In the first years of the 20th century, an American consul named Edward Thompson bought the ruined city of Chichen Itza and began dredging its sacred sinkhole, a vertical well of dark water the Maya had treated as a mouth into the underworld. He was looking for gold and sacrifice. What he eventually reached at the very bottom was a layer of blue. A bed of blue sediment roughly 4 meters thick had settled across the floor of the well, the residue of centuries of offerings painted in a single stubborn color. The blue was not decoration alone. The Maya coated temple walls with it, spread it across the great murals of Bonampak, and in their most charged rituals, painted the people and objects offered to the rain god before they were cast into wells exactly like this one. The sediment Thompson reached was, in part, the slow accumulation of sacrifice, settling for centuries in the dark water. That is why the color carries weight beyond chemistry. It was the shade the Maya reserved for the threshold between the living world and whatever they believed waited beneath the surface. That color is also the puzzle. Maya blue does not behave the way ancient pigments are supposed to behave. Almost every organic dye the ancient world produced has faded, browned, or flaked away. Maya blue has not. It has survived more than 12 centuries of tropical humidity, of acidic soil, of sun and rot, and in many cases, it looks as if it were applied last week. In the laboratory, it shrugs off treatments that should obliterate it. It resists hot nitric acid. It resists alkalis. It resists the solvents that strip every comparable colorant down to nothing. For decades, the recipe was genuinely obscure. The breakthrough came from a single combination most chemists would never have tried. Maya blue is not one substance, but two locked together. Indigo, the same plant dye used in blue jeans, and palygorskite, a humble, fibrous clay full of microscopic internal channels. On their own, indigo fades, and the clay is colorless. Bonded under gentle heat, the dye molecules thread into the clay's channels and are sealed there, shielded from the chemistry that would normally tear them apart. Dean Arnold, an anthropologist at the Field Museum in Chicago, spent much of his career reconstructing how the Maya actually performed this. With colleagues, he reported in 2008 direct physical evidence from pottery at Chichen Itza that the pigment was cooked, likely over burning copal incense, fusing dye and clay in the heat and smoke of a ritual. The making of the color was not industrial. It was an act of religion. But here's where the comfortable version of the story develops a crack. We can make Maya blue today. What we cannot fully agree on is exactly how they made it. At a meeting of American archaeologists in April of 2025, Arnold presented evidence for a second, entirely different method, one that used no copal at all, recovered from cracks and residues on a set of bowls from the same city. 2 recipes, possibly more, for a single sacred color, and the field is still arguing over which came first. What stays with you is the asymmetry of it. A culture without a modern chemistry lab engineered a stable organic-inorganic hybrid pigment by hand, a class of material science we only described in the 20th century. And they did it well enough that their blue has outlasted the civilization that mixed it. The knowledge of why it worked was lost. The proof that it worked is still sitting at the bottom of a well. But a pigment that refuses to fade is a quiet kind of marvel. The next object does something stranger. It changes color depending on which way the light is moving. Number 9. The Lycurgus cup. In the British Museum sits a small Roman drinking cup carved in the 4th century with a scene of the mythical king Lycurgus being strangled by vines. Under ordinary light, it is an unremarkable jade green. Then someone places a lamp inside it and the cup turns blood red. The same glass, the same instant. 2 completely different colors depending on whether light bounces off it or passes through it. The cup is a tour de force before the color is even considered. It is what specialists call a cage cup, carved so that the figures stand almost free of the vessel wall, attached to the body only by slender, hidden bridges of glass. The kind of cutting that takes a master months and forgives no slip. But the carving is the part we can explain. The color is not. This effect is called dichroism, And the Lycurgus cup is the only complete object from the ancient world that does it this dramatically. Beyond it, only a scattering of small dichroic glass fragments survives from the entire Roman world, which tells you how rarely even the Romans managed the trick. For a long time, it was simply a curiosity, an accident no one could explain. The explanation, when it arrived, belonged to a science the Romans could not possibly have had a name for. Scientists at the British Museum, including the materials specialist Ian Freestone, examined fragments under electron microscopy and found the cause suspended inside the glass itself. Particles of gold and silver, alloyed together, scattered through the material at a scale of tens of nanometers, roughly 50 billionths of a meter across. A single one of these particles is around 1,000 times smaller than a grain of table salt. At that size, metal stops behaving the way metal does in a ring or a coin. The particles interact with light by their dimensions alone, absorbing some wavelengths and transmitting others. So the cup glows green in reflection and red in transmission. This is, in plain terms, nanotechnology, not as metaphor. The optical behavior of metal particles a few dozen nanometers wide is the literal subject of modern plasmonics, a field that did not exist until the late 20th century. And here is the part that resists easy replication. It is not that we cannot make colored glass. It is that making this requires dispersing metal particles of an extraordinarily specific and uniform size, evenly, throughout molten glass, with no instrument capable of seeing what you are doing. Get the particles slightly too large or too small, or let them clump, and the effect collapses into murk. The Roman glassmaker who produced the Lycurgus cup almost certainly did not understand the mechanism. The likeliest explanation is that a batch of glass was contaminated with finely divided gold and silver, perhaps from scrap, in just the right proportion, and someone noticed the result was extraordinary. Whether they could ever reliably do it again is an open question. We have one complete cup. We do not have the workshop, the notes, or the dozens of failures that surely preceded it. That uncertainty matters because in 2013, researchers studying the cup's optical properties pointed out that the same principle, particles changing color in response to what touches them, could power a new generation of sensors fine enough to detect pathogens in a single drop of fluid. A 4th century party trick became a blueprint. We are still trying to catch up to an effect a Roman artisan stumbled into and could not name. A cup made by lucky contamination is one thing, but the next civilization didn't get lucky once. They mass-produced a metal that should not have existed for another 700 years, and they signed their work. Number 8. The Ulfberht swords. Across northern Europe, in graves and riverbeds and bogs, archaeologists have recovered roughly 170 Viking-age swords carrying the same strange inscription, hammered into the blade in iron letters. A name, framed by crosses, Ulfberht. They span the 9th to the 11th centuries, and the best of them are made from a steel that, by every rule of European metalworking at the time, should have been unthinkable to produce. The man who established this most rigorously was Alan Williams, an archaeometallurgist at the Wallace Collection in London, who analyzed dozens of these blades. His findings drew a hard line through the group. The finest Ulfberht swords are made of what metallurgists call hyper-eutectoid steel, steel with a carbon content of around 1.2% or higher, and remarkably free of the slag and impurities that plagued ordinary medieval iron. This is crucible steel. To make it, the raw material has to be heated until it fully liquefies, which demands temperatures and crucible technology that Europe did not possess. A European bloomery furnace of the period could soften iron into a spongy mass, but never bring it to a full melt, which is exactly why slag-riddled uneven blades were the norm. Liquefying steel to drive the impurities out was simply not on the menu. Europe would not reliably produce steel of this quality until the crucible process was reinvented in England around 1740. On the doorstep of the Industrial Revolution. So a Viking warrior around the year 1000 was sometimes carrying a blade made of steel that his entire continent would not learn to make for another 7 centuries. The most credible explanation is trade. The high-carbon ingots almost certainly traveled north along the Russian river routes from the Islamic world and Central Asia, where crucible steel was being made, and were forged into swords in Frankish workshops. The Ulfberht name was, in effect, a brand stamped on premium imported material. But here's where the story turns genuinely sharp. Williams and others noticed that not all Ulfberht swords are equal. Many are crude imitations, made from ordinary low-grade steel that would shatter or bend in a real fight, yet still carrying the prestigious inscription, just with the crosses in the wrong places. The genuine high-carbon blades carry one specific arrangement of the marks. The fakes copy the letters, but botch the punctuation. Read that plainly. More than 1,000 years ago, someone was counterfeiting a luxury weapon brand and getting the logo slightly wrong. Medieval brand piracy, preserved in steel. Of the swords that have been put under analysis, only a minority carry the true crucible steel at all. The rest are the period's knockoffs, trading on a name their makers could not back up. The lived stakes were not abstract. To the man holding it, the difference between a real Ulfberht and a convincing fake was the difference between a blade that held its edge through a battle and one that failed at the first hard parry. He could not see carbon content. He could only trust the name on the steel and hope the smith who sold it to him had not lied. What was lost here was not the swords. We have those. What was lost, for the people forging the imitations, was the chain of knowledge connecting the mark to the method. They had the brand and no idea what made the original worth copying. They were reproducing the signature of a technology they did not understand. That gap between possessing a thing and understanding it only widens from here, because the next civilization didn't make a single object. They engineered an entire city to survive in a place that should have been a death sentence for everyone in it. Number 7. Nabataean Petra. In a narrow desert canyon in what is now southern Jordan, a people called the Nabataeans built a city of perhaps 30,000 inhabitants in one of the most hostile environments on Earth. Petra receives only a few centimeters of rain a year, in violent bursts that flood the canyons and then vanish. By every logic of geography, a dense permanent population should have been out of the question there. The Nabataeans made it not only possible, but comfortable, and they did it with water engineering so precise that hydraulic specialists still study it as a working design rather than a ruin. The scale alone is hard to absorb. Across their territory, the Nabataeans built an estimated 36 dams to tame flash floods, more than 100 cisterns and reservoirs to bank water against the dry months, and roughly 200 kilometers of channels and ceramic pipe to move it where it was needed. Estimates of the system's capacity run to hundreds of thousands of cubic meters of stored water, in a place where a person today might struggle to find a drink. By some reconstructions, the network could deliver on the order of 360 liters per person per day at peak, a level of supply that would not embarrass a modern town, conjured in a canyon that sees almost no rain. The detail that impresses engineers is not the size, it is the control. Charles Ortloff, a hydraulic engineer who has spent years analyzing the Petra network, has shown that the Nabataeans sized their terracotta pipes and graded their channels to keep water flowing at a specific, stable rate, deliberately avoiding the turbulence that builds up when a pipe runs too full and too fast. Run water carelessly through a long pipeline, and it surges, hammers the joints, and tears the system apart. The Nabataeans designed against that. They built settling basins to drop out sediment so the pipes would not clog. And they balanced flow from multiple springs so the supply held steady through wet season and drought alike. These are principles taught in modern hydraulics courses. The Nabataeans arrived at them by craft, without the equations, and got them right. The most quietly brilliant feature sits at the entrance. The famous narrow gorge leading into Petra, the Seek, is also a flood trap, and the Nabataeans walled and channeled it to divert the killing surges of stormwater away from the path, so visitors and residents would not be swept off their feet by a wall of brown water arriving from kilometers away. So why is this on a list of lost technology? Because the knowledge did not survive the city. When Nabataean independence ended and the trade routes that funded Petra shifted, the integrated mastery that ran this system, the accumulated judgment of how to balance every spring, dam, and pipe across an entire watershed, drained away with the people who held it. The hardware silted up. The expertise was never written into a manual anyone could follow. Petra did not die of thirst. It died of forgetting how it had ever not been thirsty. And the warning is not historical. Jordan today is one of the most water-scarce countries on the planet, and Petra still floods. In recent years, flash floods have torn through the same canyons, drowning the very diversion logic the Nabataeans engineered around. In November of 2018, surging stormwater forced the evacuation of more than 3,500 visitors from the site, racing through the same seek the Nabataeans had spent generations learning to outwit. We now protect the ruins of their water system from the water their system was built to defeat. From bending water to bending metal at the atomic scale, the next people guarded their secrets so well that the recipe stayed buried for 200 years, hidden inside the steel itself. Number 6. Damascus steel. For roughly 1,000 years, the finest blades in the world carried a surface that looked like flowing water, bands of light and dark rippling down the steel as if the metal had been caught mid-current and frozen. This was Damascus steel, forged across the Near East from ingots of a raw material called woots, produced in India and Sri Lanka and traded west. Crusader accounts and later European travelers described blades that could hold a savage edge and flex without snapping, and the watery pattern became a signature of quality no European smith could match. The legends grew to fit the reputation, blades said to slice through a silk scarf dropped onto the edge, or to shear a lesser sword in two without a notch. Strip away the romance and a hard core remains. Even sober metallurgical testing confirms these were genuinely exceptional blades, not merely beautiful ones. And then, sometime around the end of the 18th century, the blades stopped. The chain of production broke, the source ingots changed, and within a couple of generations, no one alive could reproduce the true Woots Damascus pattern. The recipe went silent for roughly 200 years. What makes the loss so strange is what modern microscopy eventually found inside the metal. In 2006, the physicist Peter Pofler and his team at the Technical University of Dresden published an analysis in the journal Nature of a Damascus saber from the 17th century. After dissolving part of the blade in acid, they reported finding not only nanowires of iron carbide, but structures they identified as carbon nanotubes. The same cylindrical carbon architecture celebrated as a triumph of 21st century material science. Whether those structures are truly nanotubes is still debated among specialists, but the broader points survive the argument. This steel is organized at the nanometer scale in ways that ordinary forging does not produce. The likeliest explanation for how it was made points to the ore. The metallurgist John Verhoeven and his collaborators argued that the famous banding depended on minute traces of specific impurities, elements like vanadium, present in the particular ore deposits the Woots makers used. Through slow heating and forging cycles, these trace elements caused carbides to line up in sheets, producing the watery pattern. Verhoeven and the bladesmith Alfred Pendray eventually managed to reproduce the surface pattern in the laboratory, but only after hunting down ore with exactly the right trace chemistry, which is closer to forensic detective work than to inherited craft. When those specific ore sources were exhausted or replaced, the impurities vanished, and the smiths, following the same steps that had worked for centuries, suddenly produced ordinary steel. They had not forgotten the method. The method simply stopped working, and they had no way to know why. This is where the honest line has to be drawn, because Damascus steel is sold today in every knife shop on Earth. Almost all of it is pattern-welded steel, made by folding and forging together layers of different alloys to fake the surface ripple. It is genuinely beautiful, and genuinely not the same thing. The original Woots process, the crucible chemistry that grew those carbide bands and possible nanostructures from a single cake of steel, has been partially reproduced in laboratories by researchers who reverse-engineered the conditions, but it has never returned as a living craft. We can sometimes imitate the result. We did not inherit the knowledge. The detail that lingers is the helplessness of it. A master smith in 1790 could do everything his grandfather did, with the same hammer and the same fire and the same care, and watch the water pattern refuse to appear, with no concept that the answer was a few atoms of a metal no one would isolate for decades. The skill was intact. The world that fed it had quietly changed. A blade can outlast the empire that swung it, but the next material outlasts almost everything, and it does something no modern version of it can do. It heals. Number 5. Roman concrete. Off the coast of Italy, Roman harbor structures have stood in the surf for around 2,000 years. Concrete piers, breakwaters, and foundations, poured before the birth of Christ, are still intact, still holding, in the one environment that destroys modern concrete fastest: seawater. A concrete seawall built today is engineered for a service life of perhaps 50 to 100 years before salt and corrosion eat it apart. The Romans built for what has turned out to be 20 times that, and the structures are arguably stronger now than the day they cured. On land, the same material achieved something just as improbable. The dome of the Pantheon in Rome, poured around the year 126, is still the largest unreinforced concrete dome on Earth nearly 19 centuries later, a span of more than 40 meters, holding itself up without a single bar of steel inside it. No modern engineer would pour an unreinforced concrete dome at that scale and expect it to outlive their own grandchildren, let alone their civilization. For a long time, the durability was filed under Roman luck, or lost under the assumption that they simply used more material. The real answer is chemistry, and it cuts in two directions, both uncovered only recently. The first piece came from the volcanic ash the Romans mixed into their marine concrete, a material called pozzolana. The geologist Marie Jackson at the University of Utah led work published in 2017 showing that Roman seawater concrete does not merely resist the ocean, it uses it. As seawater percolates through the material over centuries, it reacts with the volcanic ash to grow new interlocking mineral crystals, rare forms including aluminous tobermarite, knitting the concrete tighter as it ages. Modern concrete is designed to be inert and unchanging, and it slowly loses that battle. Roman concrete was, in effect, alive to its environment, and it won. The second piece came in 2023. When Admir Masic and Linda Seymour at the Massachusetts Institute of Technology published findings in the journal Science Advances on the little white chunks of lime scattered through Roman concrete, long dismissed as sloppy mixing. They were not a mistake. The Romans used a hot mixing technique that left these reactive lime fragments embedded throughout the material. When a crack forms and water seeps in, the lime dissolves and recrystallizes inside the crack, sealing it shut before it can spread. The concrete repairs its own wounds automatically with no human hand involved. Self-strengthening and self-healing in a building material from 2,000 years ago. The irony is almost too neat. Pliny the Elder, writing in the 1st century, claimed that Roman marine concrete became a single stone mass, impregnable to the waves and every day stronger. For 2,000 years, we read that as a Roman exaggerating. The rocks, it turns out, had simply read his account more carefully than we did. This is not a case of vanished magic. We now understand the mechanisms in detail, but understanding is not the same as reproduction at scale. Modern construction still runs almost entirely on Portland cement, which is faster, more uniform, and far more controllable, but which crumbles in marine conditions and pours an enormous burden into the atmosphere. By many estimates, around 8% of all human carbon dioxide emissions. Engineers are now racing to build the self-healing properties of Roman concrete into modern formulas, precisely because we did not have them. We outran the Romans on speed and convenience, and we are reverse engineering our way back toward durability we abandoned. The Romans poured a material that mends itself. The next civilization didn't pour anything. They cut stone so precisely that 2,000 years and a string of major earthquakes have not been able to pry the blocks apart. Number 4. Inca polygonal masonry. Above the city of Cusco in the Peruvian Andes stands a wall built by the Inca that has defeated every attempt to fully explain it. The fortress complex of Sacsayhuaman is made of irregular limestone blocks, some weighing well over 100 tons, fitted together without a drop of mortar so tightly that the joints between them will not admit a knife blade or a sheet of paper. The stones are not cubes stacked in rows. They are many-sided, each one cut to lock against its neighbors in a complex three-dimensional puzzle, no two alike. In a street in Cusco itself sits the most famous single block, the 12-angled stone, a single piece cut with 12 separate corners, every one of them mated flawlessly to the irregular stones crowded around it. There is no mortar, no visible gap, and no margin for a second attempt. The block was shaped until it fit, and it has held that fit for roughly 5 centuries. The achievement is not only the fit, it is what the fit does. In 1650 and again in 1950, major earthquakes struck Cusco and flattened the Spanish colonial buildings the conquerors had raised on top of and around the Inca foundations. The Inca walls did not fall. Their secret is in the geometry. The irregular polygonal joints and the slight inward lean of the walls let the blocks absorb seismic shaking, shifting and grinding against one another and then settling back into place rather than toppling. The Spanish churches, built with mortar and right angles, had no such forgiveness. The Inca stones move when the earth moves and survive. The European stone shattered. Here the channel has a duty to be careful because Sacsayhuaman is a magnet for nonsense. It is endlessly claimed that the precision could not possibly be achieved without modern machinery or stranger sources. The careful work argues otherwise. The archaeologist Jean-Pierre Protzen, then at the University of California, spent years experimentally cutting and fitting Andean stone using only the hammerstones and methods available to the Inca. He demonstrated that the blocks could be shaped by patient pounding and repeated trial fitting, lifting a block, checking where it bound against its neighbor, lowering it, dressing the high spots, and repeating. And that abandoned blocks at the Inca quarries carry tool marks identical to the ones his experiments produced. Internally, many of the joints are wedge-shaped, the blocks angled inward and packed behind their visible faces, exactly what you would expect from fitting by hand rather than by some flawless machine. So the physics is not the mystery. The mystery is the scale of the human achievement, and it is genuinely unresolved. No one has matched the rate and consistency of this work with the documented Inca toolkit. Protzen proved the method was possible. He did not prove it was sufficient to produce, in a few generations, the sheer volume of perfectly fitted megalithic walls the Inca left across their empire. Without an organizational and craft mastery we can describe only in outline. What was lost is not a single trick. It is the accumulated body of skill, the trained eye, and the institutional knowledge of an empire that made the impossible look routine. The blunt truth is uncomfortable for both camps. The fringe is wrong that this required machines we have written out of history. The complacent are wrong that we have fully accounted for it. Somewhere between those two errors sits a real, unreproduced human capability. And if walls fitted by eye are unsettling, the next civilization worked the same brutal stone at a scale your eye can barely measure, finishing the inside of sealed vessels to a tolerance that still starts fights among engineers. Number 3. Egyptian hardstone vases. Beneath the step pyramid of Djoser at Saqqara, archaeologists recovered an estimated 40,000 stone vessels, and many thousands more have come from across Egypt's earliest periods. A large share predate the pyramids themselves, reaching back 5,000 years and more into the pre-dynastic era. That alone would be remarkable. What turns the vessels into one of archaeology's sharpest arguments is the material some of them are made from and the precision a portion of them display. A great many of these vases are carved from soft, forgiving stone, but a significant number are cut from the hardest rock the ancient world worked: granite, diorite, basalt, porphyry. Diorite sits around 7 on the mineral hardness scale, harder than the copper tools the Egyptians of that era are known to have used. Carving a closed vessel out of it, hollowing a wide body through a narrow neck, leaving walls only a few millimeters thick, is a staggering undertaking with a soft metal chisel and a lot of time. For the finest pieces, independent researchers in recent years have taken CT scans and structured light measurements and reported astonishing figures. Internal symmetry and concentricity, with deviations they describe as smaller than thousandths of an inch. Surfaces and tool marks they compare to machined modern work. These measurements have circulated widely. They have also not, for the most part, passed through peer review. And that distinction matters enormously because around them has grown an industry of claims that ancient Egyptians must have possessed lathes, diamond tooling, or lost high technology. The argument is not an old one. It caught fire only in the last several years, as cheap and accurate three-dimensional scanning let amateurs and specialists alike measure the vessels to tolerances no one had bothered to check before, and the internet did the rest. The established archaeology answers with a workbench rather than a conspiracy. The experimental archaeologist Dennis Stocks spent decades reconstructing Egyptian stoneworking with period-appropriate tools, copper tube drills fed with quartz sand as an abrasive, twist-reverse-twist bow drilling, stone rubbers, and borers. The copper does almost no cutting itself. It is a carrier that drags the hard sand against the stone, and the sand does the work. With these methods, Stocks bored and shaped granite. More recently, a craftswoman named Olga Vdovina hand-carved a diorite vessel using only such primitive tools, and it took her around 2 years to finish one. That single fact reframes the whole debate. The precision is real. The dispute is over how much of it the documented methods can account for, especially in the most extreme pieces, and how long it took. 2 years for one vase, by hand, is not impossible to imagine multiplied across a kingdom obsessed with stone and equipped with endless skilled labor and time. It is also not a closed case, and honest archaeology says so. The temptation worth resisting is the leap from "this is hard to picture" to "therefore machines." That a modern viewer cannot easily imagine producing a diorite bowl by hand says more about the modern viewer than about the pre-dynastic craftsman, who had a lifetime, a tradition, and a patience for stone that our species has largely lost. The genuine open question is narrower and more interesting than the sensational one. Which specific techniques produced the very finest vessels, and why does no clear record of those techniques survive? What disappears here is not the vases. It is the workshop knowledge, the hand skill refined over generations that an early civilization built around stone and then never wrote down. The next loss leaves us nothing to measure at all, only the descriptions of terrified enemies and a recipe that died with the men who guarded it. Number 2. Greek fire. In the year 673, an Arab fleet besieging Constantinople met a weapon that should not have existed. From bronze tubes mounted on Byzantine warships came a jet of liquid fire that clung to whatever it touched, spread across the surface of the sea itself, and could not be put out with water. Ships burned on the water. Men who leapt overboard to escape the flames found the flames waiting for them on the waves. The Byzantines called it simply the liquid fire. History calls it Greek fire, and it saved their empire more than once, breaking the great Arab sieges of the 7th and early 8th centuries that came close to ending Byzantium altogether. When a second enormous fleet came against the walls in 717, the same fire helped shatter it again, and the memory of ships burning on calm water did as much work as the weapon itself. Enemies thought twice about facing a navy that could set the sea alight. And then it vanished. Not because the enemy stole it, because the Byzantines guarded the recipe so obsessively as a state secret known only to the emperor and a single family of technicians, that when the chain of those technicians finally broke, the knowledge went with them. Within a couple of centuries of its most devastating use, no one in the empire could make it anymore. There is no surviving formula. There never really was one to find, because the secret was deliberately never written down in full. This is the cleanest case on this list of knowledge that is genuinely, irretrievably lost, as opposed to merely not yet reverse engineered. We have eyewitness terror. We have no chemistry. Modern scholars generally agree the base was petroleum naphtha, a flammable crude distillate, probably thickened with resin or pine pitch so it would stick and float, and possibly combined with sulfur and quicklime. But every specific reconstruction runs into the same wall. The descriptions that survive were written by soldiers and chroniclers, not chemists, and were often vague by design. The delivery system is as mysterious as the mixture. The historian John Haldon at Princeton has worked on experimental reconstructions of the Byzantine siphon, and the engineering problem is severe. To shoot a stream of flaming liquid under pressure from a ship, the substance had to be heated and pressurized in a sealed bronze apparatus, with a pump and a flame at the nozzle, all of it aboard a wooden vessel surrounded by the very fire it was projecting. A small error meant the crew burned with the enemy. Haldon's work has shown that a naphtha-based, pressurized flame weapon is plausible and can be made to function. It has not proven that any modern version is what the Byzantines actually built. There were even handheld versions, portable bronze siphons a single soldier could carry, described in the Byzantine military manuals. And on the rare occasions when an enemy captured a siphon intact, they still could not make it work. The device without the knowledge was just a bronze tube. Consider what was really lost. Not just a formula, but an entire integrated weapon system. The chemistry, the metallurgy of the pump and siphon, the pressures, the preheating, the seamanship to use it without immolating yourself, held in the heads of a tiny number of people and guarded so jealously that secrecy outlived the secret. The Byzantines protected Greek fire so well that they protected it out of existence. They won the immediate war and lost the knowledge forever, which is a strategy with an obvious flaw that no one apparently raised at the time. A lost weapon is a tragedy of secrecy. The final object is something else entirely. It is not a substance or a technique. It is a machine, dredged from the sea, that proves an entire way of thinking existed 2,000 years ago and then disappeared so completely that nothing like it would be built again for 14 centuries. Number 1. The Antikythera mechanism. Picture a fishing boat in the spring of 1901, riding the swell off the barren Greek island of Antikythera. Sponge divers in heavy bronze helmets are working a Roman shipwreck on the seabed below, hauling up bronze and marble statues from a vessel that sank around 2,000 years ago. Among the corroded lumps they bring to the surface is one unremarkable piece of bronze, green and fused with rock. It is set aside. It sits in a museum in Athens for months before the encrustation cracks open on its own and reveals, inside, something that has no business being there. A gear. A precise, toothed bronze gear, machined for a purpose, lying inside a Roman wreck from the 1st century before the Common Era. That object is the Antikythera mechanism, and it is the single most disorienting artifact ever pulled from the ancient world. It is a hand-cranked astronomical computer built somewhere around 150 to 100 years before the Common Era, containing a system of at least 30 interlocking bronze gears, some with teeth filed to a spacing of well under 2 millimeters. Nothing of remotely comparable mechanical complexity appears anywhere on Earth again for around 1,400 years, until the geared astronomical clocks of medieval Europe. What it did is more astonishing than how it looked. The decisive modern work came from a research team led by Tony Freeth and the late astronomer Mike Edmonds, who used advanced imaging to read the gear trains and inscriptions, publishing their reconstruction in the journal Nature in 2006 and a further analysis in 2008. Turn the crank and the mechanism modeled the heavens. It tracked the position of the sun and the moon through the zodiac. It reproduced, through an ingenious pin and slot arrangement of 2 gears on slightly offset centers, the moon's varying speed across the sky, the fact that it moves faster at some points in its orbit than others, a subtlety of celestial motion encoded in bronze. It predicted eclipses decades in advance, using an ancient cycle of 223 lunar months. It even tracked the 4-year cycle of the Games, including the Olympiad, on a dedicated dial. This is not a calendar scratched on a wall. It is the physical embodiment of a mathematical model of the cosmos, executed in precision gearing by Greek hands before the Roman Empire existed. And here is the part that should genuinely unsettle you. A machine like this is not a first attempt. The sophistication of the gearwork implies a tradition behind it. Earlier devices, accumulated technique, a workshop culture that knew how to do this and had done it before. We have references that fit. The Roman writer Cicero, in the same century, described bronze devices that modeled the movements of the sun, moon, and planets, attributed to figures like Archimedes. And then, silence. The entire body of knowledge that produced the Antikythera mechanism simply ends. The tradition vanishes so completely that for 14 centuries no one builds anything like it. And when Europe finally does construct geared astronomical clocks, it is starting over from nothing, with no idea that the Greeks had been there first. You are descended, intellectually, from people who could do this and then forgot. Not a lone genius's lost notebook, an entire technical lineage, extinguished so thoroughly that its single surviving product spent 2,000 years on the seabed before anyone even recognized what they were holding. The honest boundaries still matter. The core function of the mechanism is no longer in serious dispute. It is a geared model of the cosmos and an eclipse predictor, decoded gear by gear. What remains argued is the exact design of the front display and whether and how it showed the 5 known planets, with several competing reconstructions still in play. No serious scholar disputes that a Hellenistic Greek built a working analog computer. They dispute only the last details of how much it could do. The Antikythera mechanism is the clearest evidence we have that knowledge does not accumulate in a straight line. It can be reached, refined, and then lost so cleanly that the people who come after do not even know there was anything to lose. Bronze gears do not care about our story of steady progress. They sat in the dark for 2,000 years, holding a model of the sky that their own civilization had thrown into the sea and forgotten, waiting for a species clever enough to rebuild the knowledge from scratch, and humble enough, eventually, to admit it had been done before. Across all 10 of these, the same pattern surfaces, and it is not the pattern the documentaries usually sell. None of this knowledge was lost to a single catastrophe, a fire in a library, a city put to the sword. It drained away through ordinary, almost bureaucratic failures of transmission. A recipe kept secret until its keepers died. An ore deposit quietly exhausted. A workshop that closed without an apprentice. A brand copied by people who no longer understood what made the original worth copying. Knowledge survives only where 3 things hold together at once. It has to be written down, it has to be taught to the next pair of hands, and it has to be continuously used. Sever any one of those threads, and a working technology can vanish within 2 or 3 generations, leaving behind an object no one can fully explain. The modern echoes are not hard to find. We now understand Roman concrete's self-healing chemistry in detail, published as recently as 2023. And we still pour billions of tons of inferior cement that crumbles in seawater. We reverse-engineered the optics of the Lycurgus cup and are only now turning 4th century dichroic glass into 21st century sensors. We have argued over Maya blue for a century and uncovered a second ancient recipe for it as recently as 2025. The Antikythera mechanism took more than 100 years from its recovery to a confident decoding. We are, in case after case, the latecomers reconstructing what an earlier people simply knew. What the survivors and the lost civilizations had in common is worth sitting with. They were not less intelligent than we are. In their crafts, they were sometimes our equals, occasionally our superiors. The difference between a technology that endures and one that disappears was almost never raw genius. It was whether the knowledge was held loosely enough to be shared and recorded, or clutched so tightly or practiced so narrowly that it could die with a single generation. That is the real warning these objects carry. We tend to assume that anything truly important, once discovered, stays discovered. The bronze gears, the watery steel, the blue that will not fade, all say otherwise. Progress is not a possession, it is a practice, and a fragile one, kept alive only as long as someone is still doing it and still teaching it. The people on this list were not erased by the gods or rescued by visitors from elsewhere. They were ordinary, brilliant human beings who solved hard problems and then, through nothing more dramatic than forgetting, let the answers slip beneath the surface, where we are still diving to find them. If you want to see more videos like this, click the video on screen now and make sure to subscribe.